Now let's look at some common Fourier transforms. First, before we do that, let's define a couple of new signals that, some new definitions that will come in quite handy, and I'll work with Fourier transforms. One is the unit rect function, the unit rectangular function, and you'll see this indicated as either rect of t, or you also see the notation capital pi of t, but it's defined as 1 when for t less than, an absolute value of t is less than or equal to 1/2, and then it's 0 for all t. Absolute value of t greater than 1/2. So a graph of this function just looks like this. It's 1 for t between -1/2 and 1/2. So this is the rect of t. You might also see something like this, rect of little t over capital T. So in this case, the unit rect has a width of 1. T over t is a function that has a width of capital T, so it actually goes from -t over 2 to plus t over 2. Again, would have a height of 1, and notice if I substitute in t is equal to t over 2 here, I'll get rect of 1/2, which is this edge. And then actually related to that is unit triangle. You'll see a couple different definitions for this in various textbooks, but in this book it's defined as being 1 minus 2 times the absolute value of t for t less than 1/2, and it's 0 for all t greater than 1/2. So what this function looks like is has a peak amplitude of 1 at t equal to 0, and then at 1/2 it's back at 0, so it's a straight line, and then also and in this textbook the triangle function is also defined as having a width of 1. In some books it's actually defined as having a width of 2, and it's the result of actually convolving the rect, the unit rect with itself, but we'll use this definition in this textbook. And then there's another function that appears quite often in our Fourier transform work. It's called the Sinc function, and it's defined in our textbook. Sinc of t is the sine of t over t. You have to use L'Hopital's rule to actually evaluate this at t equal to 0, because we'll have 0 over 0 in an indeterminate form. If you use L'Hopital's rule and evaluate that, this turns out to be equal to 1. It's well defined for all the values of t, and then since sine of integer multiples of pi is equal to 0, then the sinc at n pi values is equal to 0. It's kind of enough information to at least come up with a rough sketch of the sinc function. We know at 0 it's equal to 1, and then at pi it's 0, at minus pi have another 0 crossing, at 2 pi it's 0, at minus 2 pi it's 0. Sinc function will look, it's a sine divided by t, so as we go farther out, as t gets larger, as we're dividing by t, the sinc function will get smaller and smaller, but it's oscillating here. So, and then these oscillations get smaller. Sine is an odd function, as is t. The ratio actually is an even function. So the sinc function will have even symmetry. So sinc of minus t is equal to sinc of t. Okay. So this is a rough sketch of what the sinc function looks like. One thing you will have to be careful with is that in Octave and MATLAB and in some other text, you'll see a different definition for the sinc function. The sinc is defined in those texts or as sine of pi x over pi x. Our definition is related to the MATLAB definition. Ours is, we call ours S sinc of t. It's going to be the MATLAB definition. It's going to be sinc of actually t over pi to get the same definition. So in the UE toolkit for MATLAB and Octave, there is this definition of S sinc that is consistent with our textbook's definition of the sinc. Okay. So now let's look at some additional Fourier transforms now that we talked about a few new signals. Let's talk about the Fourier transform of x of t is rect of t over tau. So what this looks like is a pulse that goes from minus tau over 2 to plus tau over 2. Again, just remember that it's centered at the origin and has a total width of tau. That will help you to remember that it goes from minus tau over 2 to tau over 2. And then so the Fourier transform of this function we can evaluate directly from the definition of the Fourier transform, the interval from minus infinity to infinity of x of t e to the minus j omega t dt, or in this case, since this is only non-zero between minus tau over 2 and tau over 2, and it's 1 within this region, and we integrate this and evaluate it at the limits, we'll get e to the minus j omega tau over 2 minus e to the plus j omega tau over 2. This is 1 over j omega times 2j sine of omega tau over 2. From an application of Euler's formula, the sine is 1 over 2j e to the plus j minus e to the minus j. So I factor out the minus sign here. I've got the 1 over j omega, and so this will become 2j sine of omega tau over 2. Or the j's cancel, and I'll have 2 over omega sine of omega tau over 2. This is often written in the form of our sinc function, so I can get it in that form by dividing by tau, and so I'll have 1 over omega tau over 2 times the sine of omega tau over 2. This becomes then tau of sinc of omega tau over 2. So the Fourier transform of that rectangular pulse is tau sinc of omega tau over 2. This is one of the few cases, well, that's not true. can be true anytime x of t has even symmetry. But in this particular case, x of omega is entirely real, and so we can actually sketch it directly. I'll do that on the next board. So in this case, it actually has at it's a function of omega now. At omega equals 0, it's going to have a height of tau, as we have tau times the sinc function. And recall that this will be equal to 0 when omega tau over 2 is equal to integer multiples of pi. So that's going to occur when omega is n times 2 pi over tau. So first zero crossing will be at omega equal to 2 pi over tau, and then multiples of that, 4 pi over tau, 6 pi over tau, and so on and so forth. And again, that gives me enough information to kind of get a rough sketch of the sinc function in here. And it does have even symmetry. Theoretically continues on forever, although remember the absolute amplitude of the sinc function is decreasing. Alternatively, you could sketch the magnitude in phase. It's rather trivial in this case, since x of omega is entirely real, but it does go negative, so I just have to sketch the absolute value of the function. So that's going to look like this. Okay, and then these humps would go on forever. And then the phase angle for the sinc function, positive, phase angle is 0, so it's 0 in this region. And then when sinc of tau goes negative, the phase angle jumps to either plus 180 or minus 180. Show it here as minus 180. And then it's usually drawn with odd symmetry. Okay. And then in this next region, where the sinc function is positive, the phase angle is 0 again, and then for the next lobe it would be down at minus 180. And so then this picture would continue. There's one thing to notice is that it's called the null bandwidth of this sinc function, or the width of this function out to where it first crosses 0, is 2 pi over tau. So the bandwidth of the spectrum is 2 pi over tau. Here I'm using the null bandwidth definition and not the 3 dB bandwidth. But this is inversely proportional to the width of my pulse, which is pulse width is tau. So what this means is, as my pulse gets wider, the bandwidth of the spectrum actually gets narrower. So this 0 crossing would move closer and closer to omega equals 0 as tau gets larger and larger. And this is a phenomenon we'll see with other signals as well, that the pulse duration and the bandwidth of the signal are inversely proportional. The wider the pulse, the narrower the bandwidth. The narrower the pulse, correspondingly, the wider the bandwidth of the signal.